Okay, so hi everybody. So today we're going to continue going on number 3 and number 4 from the differential equations Euler's method packet. Okay, so here we go. Okay, so you have this. Consider the differential equation dy dx equal to 2x minus y. On the axis provided, sketch a slope field for the given differential equation to 6 points. Okay, so this I'm going to list out the points here. I'll make a little table here. So this is going to be the points. So this is 0, 2. 0, 1, 0, negative 1, 1, 2, 1, 1. That's supposed to be a comma. And then 0, negative 1. Okay, so plug it into this equation. You have 0 minus 2 is going to give you negative 2. 0 minus 1 gives you negative 1. 0 minus a negative 1 gives you positive 1. 2 minus 2 is going to give you 0. 2 minus 1 is going to give you 1. And 0 minus a negative 1 is going to give you, hold on, should be 1, negative 1. So 2 minus a negative 1 is going to give you 3. So all we need to do is go to these individual points and sketch in approximately what those slopes would be. So negative 2 might look something like this. Negative 1 would probably look something like this. At negative 1, it's going to be 1, so it look like this. At 1, 2, it's 0, so flat across. And then this would be positive 1 right here, right? And then 3, you just have to make sure it looks steep. Okay, and that's it. Okay, find the second derivative of y with respect to x in terms of x and y. That's important there. And determine the concavity of all solutions. Okay, so all I need to do is take the derivative of this up here. So I'm going to have the second derivative of y with respect to x is equal to the derivative of 2x with respect to x is just 2. The derivative of y with respect to y is minus dy dx. Now, what is dy dx? Because it says it wants it in terms of x and y, not dy dx. So this is 2 minus dy dx, which is 2x minus y. So this gives me 2 minus 2x plus y. Now, it states, determine the concavity of all solution curves for the given differential equation in quadrant 2. So in quadrant 2, the x's are less than 0 and the y's are greater than 0. So if I take a value that's less than 0 and plug it in here, I'm going to take a negative times a negative. That will turn positive, positive, positive. So in quadrant 2, the second derivative of y with respect to x is always going to be bigger than 0, which means this implies that the solution curves are all concave, since it's greater than 0, up in quadrant 2. Okay, that's it. C. Let f of x, let y is equal to f of x be a particular solution. That means it works in the differential equation. To the differential equation with the initial conditions, f of 2 is equal to 3. Okay, so that's a coordinate 2, 3. Does f have a relative min, relative max, or neither at x equal to 2? Well, just plug this point into the derivative and let's see what happens. Okay, so 2x minus y is the derivative. So you have the derivative dx dy evaluated at the coordinate 2, 3. So that's going to be equal to so this is 2 times 2 minus 3, which is 4 minus 3 gives you 1. Well, that's nothing, right? So since the slope of the tangent line at x is equal to 2 is 1, there is neither a relative min or max at that point. Okay, so pretty simple. Okay, D, find the values of the constant m and b for which y is equal to mx plus b is a solution to the given differential equation. So it's a solution to the given differential equation. So when you plug it in, to dy dx is equal to 2x minus y, it should work. So what is the derivative of y with respect to x? M and b are just constants, so that is m is equal to 2x minus y, but y is mx plus b. What in the world do we do with this now? Okay, so the key to doing this is noticing that there aren't any x's on this side of the equation, but there are some x's here. So what I'm going to do is I'm going to subtract it over. So if 0 is equal to 2x minus mx minus b minus m. I'm going to factor out an x here. So 2 minus m minus b plus m. Okay, so if all we have to do now is compare and contrast. There aren't any x's over here. That means 2 minus m has to be equal to 0. Therefore, m has to be equal to 2. And then furthermore, the constant term is equal to 0. So I know b plus m must be equal to 0. But m is equal to 2, so you have b plus 2 is equal to 0. b is equal to negative 2. So there we are. Okay, number 4. Consider the curve given by this equation. It can be shown that the derivative is equal to this. Write an equation for the line tangent to the curve at negative 1, 1. So I need a point and a slope. Look, there's a point. Here's an equation for the slope. So plug it in. So dy dx evaluated at the point negative 1, 1 is equal to, just plug it in here. So I have 1 all over 3 minus a negative 1. So I have 1/4. So that gives me the equation y minus 1 is equal to 1/4 x plus 1. Okay, B, find the coordinates of all points on the curve for which a line tangent to the curve at the point is vertical. So that means it's a vertical line, which means its slope is undefined. So if you go back up to the equation and you want to know where this thing is undefined, well, it's where the denominator is equal to 0. So you plug it in. So go 3y squared minus x is equal to 0. So you have x is equal to 3y squared. Okay, but that doesn't tell me any of the coordinates. I need to know a coordinate. So you can't solve one equation with two unknowns. You need another equation. So I need to look for another equation. And there it is. Okay, so I'm going to take this relationship and plug it into that equation. So when I do, I have y cubed minus x, but x is 3y squared, times y is equal to 2. So just continuing along, I have y cubed minus 3y cubed is equal to 2. Negative 2y cubed is equal to 2. Y cubed is equal to negative 1. Y is equal to negative 1. Now that's what the y value is. I still have to figure out the x value is, so just plug it back into this equation. So you have x equals to 3 times negative 1 squared, x is equal to 3. So the coordinate is 3, negative 1. Okay, and the last page. Okay, so evaluate the second derivative of the point on the curve where x equal to 1 and x equal to negative 1 and y is equal to 1. So I know from the other side I have dx dy is equal to y all over 3y squared minus x. So go through and take the derivative. So the second derivative with respect to second derivative of y with respect to x is equal to, I have to use the quotient rule. So low d high, and I'm taking the derivative of y with respect to x, so that has to be dy dx, minus high d low, so 6y dy dx, and then the derivative of x with respect to x is just 1. All over low. So 3y squared minus x squared. That looks like a whole load, but it's not too bad. All I have to do is plug in negative 1 and 1. But the question becomes, well, what about this and that right there? Do I know what dy dx is at the point negative 1, 1? Okay, do I know what it is? Well, it turns out that I do because I did it on the other side. It's equal to 1/4. So this is equal to 1/4. So plug everything in. So 3, so y is 1, x is negative 1. So 3 minus a negative 1, so plus 1, times 1/4 minus 1, 6 times 1/4 minus 1 all over 3 minus a negative 1, so plus 1 squared. So this would be 1, this is 1, minus 3 halves minus 1 all over 16. So this is a half over 16, which gives you 1/32. Okay, so that was 3 and 4 for the differential equations Euler's method packet. Okay, thanks very much. Have a good one.